Good morning, everyone. Anyway, my name is Jomark Viomandak, your subject teacher for today. But before anything else, I just wanted you to remember Philippians 4:9. Whatever you have learned or received from me, or heard from me, or seen in me, put into practice. And the God of peace will be with you. Once again, class, good morning. Anyway, our topic today is all about the three basic gas law. Before we proceed to that, let's have a recap first. Our activity is in the titled Don't Turn the Page Yet. Okay, grade 10, are you ready? Then that's great. Now let's begin. The first question is that what is the relationship between pressure and volume at constant temperature? Okay, Alex. Very good. Now, how can we calculate the final volume of Boyle's law? Yes, Karen. Absolutely. We can also use B2 is equal to B1 times B2 over B2. Since all of you are very good, you remember a lot to our last topic. Congratulations. And now, let me introduce to you the four manipulated variables in a different gas form. First is temperature, second is pressure, third is volume, and the fourth one is moles. To see how unknown variables affect one another, we have to hold the two variables, which is constant. First one, let atom relationship pressure and volume, where hold moles and temperature constant are using steel container and a constant temperature. When we decrease the volume, the pressure increase. This is an inverse relationship, which means the variables will in the same sudden equation and constant will be on opposite. Here's the equation proficient in volume. What do you think? Yes, that is P1 times B1 is equal to Kelvin. Now, to see the Boyle's law where it's coming from, we need to look at the starting pressure and volumes. And finishing pressure and volume mathematically, we can use a substitution. For that is to protest two equations together. Why? Yes, it is because the both is equal the same value. Key and magic. We have Boyle's law. Let's try using it. It is a problem. A drainage is filled with air to 60 ml atmosphere, then the drainage is sealed and compressed to 20 ml. What is the final pressure? Okay, Alan. Well, that's great. Through using Boyle's law. And it is a P1B1 is equal to P2V2. Your car's drainage, the equation now or after filling numbers, it doesn't matter. But bringing this, I want its drainage now. With the final pressure or P2, so I'm gonna get that isolated by dividing both sides. P1, B1 is over B2 is equal to P2, V2 over V2, divided it by V2 is equal to P1, B1 over B2 is equal to P2. Have you ever put a balloon on freezer? Put it out in a few hours and you found a usual balloons. As a warm up, it's come back to a full size. A temperature goes down and the volume goes down. This is a direct relationship. This is essentially the same the Gay-Lussac law except for using volume instead of pressure. Volume is equal to temperature times Kelvin. If you rearrange the equation, it is volume over temperature is equal to Kelvin. And substituted V1 or volume 1 over temperature 1 is equal to Kelvin. Volume 2 over temperature 2 is equal to Kelvin. You get the Charles law, volume and temperature. V1 over T1 is equal to V2 over T2. There's a problem. A balloon is filled with 1.5 liter of air at 20 degrees Celsius. The place is in a freezer until it reaches a temperature of 5 degrees Celsius. What is the final volume? Very good. Well, let's rearrange the Charles law. That is Charles law. T squared, T2 times V1 over T1 is equal to V2 over T2 times T2. So, divided it by T2 is equal to V1, T2 over T1 is equal to V2. To find V2, then we can plug our data. After we convert Charles to Kelvin, of course, 1.5 liter times 278 Kelvin over 293 Kelvin is equal to V2 is equal to 1.4 liter, which makes sense. Because volume and temperature are directly related, take a look at Boyle's law, Gay-Lussac's law, and Charles' law together. P1 V1 is equal to P2 V2. That is the Boyle's law. The second one is P1 over T1 is equal to P2 over T2. That is Lussac's law. And of course, the Charles law, V1 over T1 is equal to V2 over T2. We can combine these three laws as long as we hold the number of moles constant. Like P1 V1 over T1 is equal to P2 V2 over T2. Amazing. Look, try a problem with this. So, calculating the combined law, 5.36 liters of nitrogen gas are at 25 degrees Celsius and 733 millimeter mercury. Hg, what would be the volume at 128 degrees Celsius and 1.5 atm or atmosphere? We are trying to find the final volume. So let's rearrange the equation first. To get the V2 alone, T2 over P2 times P1 V1 over T1 is equal to P2 V2 over T2 times T2 over P2. We multiply both by P2 over T2, and when we clean this up, it is a free equation. T2 P1 V1 over P2 T1 is equal to V2. Now we can introduce our data. 401 Kelvin times 733 millimeter Hg times 5.36 liter over 1140 millimeter times 248 Kelvin, and turned it out to the calculation, and we get the V2 is equal to 5.57 liter. So that's it. That is the result of the V2. And now, let's proceed to the early scientists explored the relationships among the pressure of a gas, P, and its temperature or volume, and the amount N by holding two of the four variables constant among the temperature. Example, varying a third such as pressure and measuring the effect of the change on the fourth, in this case volume. The history of these discoveries provides several excellent examples of the scientific method. The relationship between pressure and volume, Boyle's law, as the pressure in a gas increases, the volume of the gas decreases, because the gas particles are forced closer together. Conversely, as the pressure in a gas decreases, the gas volume increases because gas particles can now move farther apart. whether balloons get larger as they rise through the atmosphere. Uh, whether balloons get larger can now move farther apart. So, let's proceed to the Boyle's experiment using a EG-shaped tube. To determine the relationship between gas, pressure, and volume, initially the gas is at a pressure of 1 atmosphere is equal to 760 mmHg. The mercury is the same height in both the arm containing the sample and the arm open to the atmosphere. Its volume, if enough mercury is added to the right side to give difference in height of 760 millimeter between the two arms, the pressure of the gas is 760. Atmospheric pressure plus 760 millimeter gas, 1520 millimeter gas, and the volume is V over 2. If an additional 760 millimeter is added to the column on the right, the total pressure in the gas increases. So, that was the relationship between temperature and the volume. Okay. The first experiments to quantify the relationship between the temperature and the volume of gas were carried out in 1783 by an avid balloonist, the French chemist Jacques Alexandre César Charles, 1746 to 1823. Charles' initial experiment showed that a plot of the volume of a given sample of gas versus temperature in degrees Celsius, a constant temperature is a straight line. Similar but more precise studies were carried out by another balloon enthusiast, the Frenchman Joseph Louis Gay-Lussac, 1778-1850, who showed that a plot of volume versus temperature was a straight line that could be extrapolated to the point of zero volume, a theoretical condition now known to correspond to negative 273.15 degrees Celsius. And of course, I just wanted to ask all of you about the Charles and Gay-Lussac's findings and its relationship between amount and volume. And of course, the Avogadro's law. We can demonstrate the relationship between the volume and the amount of gas by filling a balloons. We added more gas, the balloons get larger. The specific quantitative relationship was discovered by the Altin chemist Amedeo Avogadro, who recognized the importance of Gay-Lussac's, who were combining volumes of gases. In 1811, Avogadro postulated that gases contain the same number of gaseous particles. This is the historic Avogadro's hypothesis. Overall, the volume of a gas is inversely proportional to its pressure and directly proportional to its temperature, and the amount of gas. Boyle showed that the volume of sample of a gas is inversely proportional to its pressure. Boyle's law, Charles and Gay-Lussac demonstrated that the volume of a gas is directly proportional to its temperature. In Kelvins at constant pressure, Charles' law and Avogadro postulated that the volume of a gas is directly proportional to the number of moles of gas present. Avogadro's law. Plots of the volume of gases versus temperature extrapolate to zero volume at 273.15 degrees Celsius, which is absolute zero, implies that the volume of a gas is directly proportional to its absolute temperature. So, in the application, I just wanted to give the problem, and this is your assignment as well. So, let's go to the assessment sites. I just wanted you to uh, solve the problem. Show your complete solution. The problem is goes like this. A high altitude balloon is filled with 1.41 times 10 to the power of 4 liter of hydrogen at a temperature of 21 degree Celsius, and the pressure of this is 745 torr. What is the volume of the balloon at height of 20 kilometers, where the temperature is over 48 degrees Celsius and the pressure is 63.1 torr? Okay, Jeanette, very good. That is the 1.41 times 10 to the power of 4 liters. And 21st degree Celsius is equal to 249 K, 63 torr. That is the exact given. 745 torr is 48 degrees Celsius is equal to 225 Kelvin. So, 745 torr times 1.41 times 10 to the power of liter divided to 249 Kelvin is equal to 63.1 torr over 225 K. That is correct. The answer is V2 is equal to 127,400. That is the correct answer. So, above all else, congratulations class for your learning today. And that would be all. Thank you for listening once again. Good morning.